Okay, so it's a pleasure to have Vítor Vasconcelos, who just joined UVA recently. And he's going to tell us about his work on coordination in polarized societies. Go ahead.
Thank you, Jacome. It's very nice to be here. Thanks everyone for being here. This is actually the first talk I give while I'm in Amsterdam. So I'm really excited to share some of the research that I'm doing. I was told this was kind of an informal talk, so this is kind of a few projects stitched together. Well, they're all part of a big project, but most of these things that I'm going to talk about today are ongoing work. So I hope it'll be interesting for you. Is it moving, the slides?
Yes.
Yeah, all right, great. So I wanted to start by sharing with you this information that was collected by the Pew Research Center a while back that shows that there is an increase in polarization. Here I think this image is quite interesting for me. I don't know what you think about it, but what we see is that if we collect the opinions of people about certain issues, and then we rank them according to some scale that goes, in this case, from a liberal to a conservative stance on these issues, we can see that over time, this polarization is increasing. For me, this kind of information is super interesting, and but it poses a lot of questions, right? Because we're seeing that, of course, there is a distribution of opinions. That is not surprising, and that distribution is kind of moving around. But I feel like it poses more questions than it really answers anything. So just to think about that image a little bit more conceptually, what we see is that over time, this distribution is kind of becoming more and more bimodal. So what we have, I don't know if you can see my mouse. You see the cursor?
No, we can't. Is this Keynote?
It's PowerPoint. What about
now? We can. Now we can.
Okay. So what you see here is over time, you have some distribution of opinions, and it's becoming more and more bimodal. But you can think that in the beginning, there is some kind of consensus, right? And as time, because everyone has the same opinion, and then at some point, you basically have a population with two opinions. And of course, the fact that this one is in the center, it doesn't really mean much because all these divergence is relative to some state. So another question that this doesn't show is how this distribution exists in the social fabric, right? So if we think of a network of people, how are these opinions distributed throughout the people? So I'm going to pose a series of questions that I'll be discussing a bit about throughout the talk. And the first one is, well, thinking about just a simple context of diffusion of ideas, what do we expect? Do we expect consensus? So is it surprising that we have a polarized society? Or do we expect polarization? What kinds of polarization do we expect? Try to set up some basic understanding of this system. And of course, part of it will be, okay, how do these opinions are actually part of the social network, right? Because it's not just about how that there are different opinions in a network, but also how they are distributed. A second question has to do with, well, is polarization good, or can it be good? Is it bad? So what I want to ask is how the different types of polarization that we observe in the world can be positive or negative in terms of the ability of societies to coordinate. And in particular, we will see that, well, polarized societies, of course, create these kind of, you know, the echo chambers that we hear about many times, and that creates some kind of partial information, biased information. So the last part of this talk, if we have time, will be generalizing these concepts of biased informations and see how that can impact people's ability to coordinate into a desired outcome. So starting from the beginning, I'm going to talk about this idea of a very general concept of propagation of conflicting information. The main or one of the main questions of this work was related with interventions, but I will skip that for the purpose of this talk. And this is a work that I developed with Simon Levin from Princeton University, professor of ecology, a professor of data science from the University of Lisbon, and now we're working with an undergrad exploring some little facts about these kinds of systems at the UVA. And so one of the main concepts of the diffusion of ideas and technology and behavior and opinions, more relevant for polarization, is the concept of complex contagion. And to talk about complex contagion, of course, I will start by looking at the simple contagion. Simple contagion happens whenever two individuals meet and there is a probability that one of them acquires the state of the other. So the most simple and the example that it's in everyone's mind at this point is, of course, the propagation of a disease. So when two individuals meet and one of them is infected, there is a probability that the susceptible one is infected. And the more infected individuals you have, the higher the probability that you get contaminated. But of course, the acquisition of information or opinions or even technologies, so things that are risky or controversial or costly, they require multiple reinforcements from multiple neighbors so that you kind of change your own state. And people have coined this as complex contagion. It typically is studied in the context of these cascading effects. So you have individuals that have a certain threshold above which they change state or they acquire this information. And people study if this information kind of propagates throughout the network. So in the simple contagion case, you would have an individual, and then this individual can propagate its ideas through the other, and then you see how long it takes for the whole population to acquire this information. So a more formal way to distinguish between simple contagion and complex contagion is to write the probability that you kind of change your state, so acquire this information, opinion, as a function of how many of your neighbors have that opinion. So in simple contagion, you can think that this is a linear response. So the more people have that information, or in the case of infectious diseases, the more people infected, the higher the probability of switching states in a linear fashion, so proportionally to the number of infected individuals. For complex contagion, typically what we have is that there is a unit step function, so a threshold function that gives you this response. So if only a few of your neighbors have this information, you don't really acquire. If a lot of them have the information, then you acquire that information. Of course, reality tells us an intermediate story. So here we see some data from the probability of adopting Skype, given the number of neighbors that you have that also have Skype. And what you see is that instead of this linear response, and instead of this very sharp transition from 0 to 1, what you have is kind of a nonlinear response still a monotonically growing function, but it's mostly a nonlinear response. And what I will show you is that this nonlinear response is actually what originates all the phenomena of complex contagion and the phenomena that distinguish complex from simple contagion. Well, but in the context of polarization, we are interested not only on how one idea propagates or one opinion propagates, but how multiple opinions propagate in a social system. And of course, you could think that the probability that you change your state depends on your current state, right? So if you already believe something, maybe it's harder for you to change to the opposite strategy. So what we did was to, in a very stylized and simple way, that we could actually treat analytically at first, we designed a family of processes that that are inspired from the empirical data that we saw, but that also range from this complex contagion phenomena to or from simple contagion to complex contagion. And what we have is, with a single parameter, we control how concave or convex this probability of adopting a certain opinion is. So if we have simple contagion, which corresponds to this alpha parameter being 1, you have a linear response. If this alpha parameter, which we can call, I guess, complexity of adoption, if it's lower than 1, that means that it's very easy for the individual to change strategy, because it only takes a few neighbors for the individual to change strategy with a high probability. And if this complexity of adoption is larger than 1, then you require a lot of reinforcement for you to change strategy. So this defines a family of response functions. We actually studied a broader family, but I think this one captures all the main ingredients that we'll need. An interesting parallel is that we can have this empirical interpretation where we saw the data that looks like this concave distribution, but to relate to the theoretical framings that people have used many times, we can see that, for instance, a low complexity curve, so this one that has the concave curve, corresponds to a distribution of thresholds in the population that is mostly low. So most people have low thresholds in the population, so they are very likely to change behavior. A simple contagion process corresponds to a uniform distribution of thresholds, all randomly distributed throughout the population. And this convex, I might be swapping these names, I never know. The one pointing up corresponds to a distribution of thresholds that where the population mostly has high thresholds. And this is quite nice, right? Because now we don't have these problems of initial conditions that come with the fact that the rule of update is deterministic, which was the case with threshold models. I see there's a question. I don't know what's the usual behavior.
People can just ask. Yeah.
Oh, okay. It was a private thing. All right. So with this, we have basically we can span a whole range of behaviors for this system with 2 parameters. One that determines the complexity of adopting state A when you're in state B, and one that controls your response function when you have the opposite state. So here it's the parameter space, the full parameter space, 2 parameters, and we can split this space into 4 regions. One where we are, for instance, both oops, let me just pick that 1 second. Back. So we divide this into 4. You don't see my pointer anymore, do you?
No, we don't. Now we do.
There you go. So here you see that both technologies or both opinions are hard to adopt. Here they would be both low or harder than simple contagion. Here they're both easier than simple contagion. And then here one is harder and one is lower. And with it, we can look at the dynamics of the whole population now and see how the whole population behaves. So if we draw on the x-axis, let me answer that again. Sorry. This is what you get when you're still moving in the middle of pandemics. Things keep arriving. So, laser pointer. So if you plot the dynamics of the population, say in the x-axis, you see the fraction of individuals adopting opinion A, say, and in the y-axis, you plot the most likely direction of evolution of the system. Then you can see, well, the first obvious result is if the adoption of opinion A has a complexity that is less than simple contagion, then and the other one has a complexity that is higher than simple contagion, then you get dominance of behavior A or opinion A. Of course, all of this is symmetric. And then the two most interesting cases that relate to polarization are these ones. So in the bottom left, we have a case where we do expect some coexistence of the two opinions. So independently of where you start, you expect to end up in an intermediate configuration where there's no consensus. So we could, if we go back to that picture of the distribution of opinions, we expect to see two opinions in the population. And here we have what I called consensus with these, what do you call these? Well, with these things, air quotes. With quotes. And depending on where your population starts, you expect it to go to a consensus of either opinion B or opinion A. And this is really nice, and we can do all these analytical calculations because we assume that everyone, that we have a well-mixed population and we can make it finite or infinite. It doesn't really matter, but it's well-mixed, right? And this is not what reality is, but it gives us a really solid ground to understand the behavior of the fuller system. So what I'm going to show you next is then the role of having a social structure. And of course, we can start, for instance, with the most basic social structure, which is a lattice. And if we look at these two regions, one that is the polarization, where we expected the coexistence, and one that it's the consensus, where we expect coordination into either A or B, what we see is that over time, we start getting these clusters of opinions, but here the cluster in the polarization case, the cluster of opinions, the cluster size remains more or less fixed, Whereas in the consensus regions, these clusters start growing until eventually one of them takes over the other. So if I were to draw a stylized figure for the behavior of this, we would see, well, the dominance of, in that parameter space that we were talking earlier, we would see either the dominance of one opinion, the dominance of another opinion. Here we would see kind of a more mixed and dynamic change of opinions. And here we would see these clusters that eventually take over one or another.
Sorry, can I just ask a question? What are the rules you use to evaluate?
So the rule is just this or this. So you look at your neighbor. So let's say you are a blue individual. Yeah, I skipped over this. Say you are a blue individual. You look around your network and you see how many of your neighbors are red. And the probability of changing to red is just given by these functional forms. Okay. So if it's simple contagion, what you get is a straight line. So the more the probability is proportional to the number of red individuals. If we have a more complex adoption process or complicated, maybe that would be the right word. Then you have this gray line where alpha is bigger than 1. And if it's simpler, then you get this orange line. Okay? And this is the whole.
But where is like this sounds very similar to Schelling's model, right? I mean,
it's quite similar, but it includes the non-linearity, right? On the number of neighbors.
Okay.
And that's exactly the interesting part, I would think, because it's this. So if you think of the simple contagion processes, the linear processes, what they have is that they exist in this line here, one of these lines, or actually they exist in this point, which is a very degenerate case, and we are exploring these, other responses.
Can I ask a quick question?
Yeah.
Sorry, I was disconnected. Maybe you explained and I forgot. I missed that. So in the log curves that you just showed, that nonlinear and linear one. So the curves that you just showed. So it's just an assumption, or I mean, is based on something. So I'm trying to make an analog between physical dynamical systems. So is it you just assume that the more people around you, you basically get more contaminated? Is that the case? Or there's let's say, experimental evidence for it too?
So both. So we did try basically we can get the results as a function of this response form, but this is one experimental evidence that you have for the probability of adopting Skype as a function of the number of neighbors that you have adopting Skype. There is very similar, some more convex examples on, or concave examples what is it? I think it's the production of certain products. So people design these networks that are made of countries, and the neighbors are basically the trading partners. And you can see the adoption of basically a production, a large-scale production at the country level as a function of the number of neighboring countries that have the same kind of production level. Scales kind of in this way. So it's basically just generalizing, taking this empirical as a way to motivate a more general response function.
Understood. And all of it, at least so far, is only with one variable. So in principle, you can make a dynamical system as multivariable and
exactly. Well, in this case, we're looking at So for this data, it's the adoption of one technology, assuming you will probably have the same. So what we did was think of two, which is the minimum that we need to get some kind of coexistence of two opinions. And of course, the idea will be to generalize this to more strategies. Yeah, that would be great.
Excellent.
So this is just the bare minimum. And now here, just for illustration purposes, if I just put, I don't know, 1,000 times 1,000 individuals on a lattice and gave them different, different shapes for these functions, so we can see kind of what is happening. And what we see here is that this polarization regime is a lot more dynamic. You can see that individuals keep changing strategy, where this, where you still have some kind of coexistence, it's much slower, right? And you start getting these big clusters. And so, of course, we can measure many properties of this system. Here, I'm showing you the average time that it takes for a finite population to reach consensus. And of course, in the polarization region, where you expect to always have the two opinions coexisting, this average time goes to infinity. And what we did was that we tested a bunch of different types of networks. For instance, a random homogeneous, scale-free, and then the modular network. And the modular network is actually the most interesting case because, well, of course, there are some quantitative differences between the well-mixed and the networked version of the model. But the most interesting is what happens with the modular networks when you get into this consensus region, right? Where there seems to be an explosion of this time to reach consensus when you get these modular networks. And this, once you see it, it's kind of neat because what we called consensus before is actually what generates this structural polarization, in the sense that if you have kind of well-defined, or if the process somehow generates this well-defined modules, then you expect that these clusters to be isolated in these modules. So, and then it's very hard for one of them to take over the other. Whereas what we defined as polarization in the well-mixed model, it's actually a much more dynamic, even though both could end up in the same distribution of behaviors, right? Like what we saw in the first figure, where you do have two opinions in the population. These are very, very different, right? And so just to conclude a little bit on this part of the talk, well, we're halfway through. With this very simple and stylized approach, we're able to see the coexistence of these two opinions, but also we can see that these are structurally different kinds of polarizations. So one of them is very dynamic, and we see the coexistence of different opinions in the network in a very dynamic fashion. The other one is a more structural polarization, where basically the dynamic freezes or almost freezes once you get your modules in a local consensus. So, yeah. And well, now that we have a good sense of what can originate these different types of polarization, we wanted to ask if and when polarization is good or bad for society, right? Because it's not obvious that if we have a distribution of opinions, or that's necessarily bad for anything, right? So what we wanted what we did was in a collaboration with well, experimentalists from Kassel University, Astrid and Marcel, and basically psychologists from Princeton University, Sara and Elke, and Simon Levin, also a professor of ecology at Princeton. Well, we tried to answer this question. So does polarization affect behavior? Because that's what, in the end, is the most interesting part of polarization, right? And more particularly, does it impact society's ability to coordinate into some desired outcome? And for that, we need to dig a little deeper and go into the literature of polarization. We see that people do discuss these different types of polarization that I kind of hinted at in the previous section. So what we saw in the first image of the distributions of opinions kind of splitting apart has to do with issue polarization. It's just the fact that the distribution of opinions in the network is getting more bimodal. The second has to do with affective polarization, which is related to identity and more precisely related into how one group judges another one. And of course, this is closely related to these modular structures that we see. So then we want to see how these affect, for instance, the perception of outcomes of different actions. So you could think that if you have an opinion about a certain issue, that will change how you perceive the outcome of a given action, say climate change, for instance. If you believe that it's man-made, then of course your action will have a different impact than you will believe that your action will have a different impact than if you don't. But also the perception of what others' actions will be, that's what in the end creates your behavior, right? Because if no one else is willing to do anything about climate change, for instance, then it's also not in your own interest to do anything about it. And of course, affective polarization then interacts with these two. So our approach was to devise this model, make some predictions with this model, and then do some experiments. We just got some results of the experiments this morning, and I made a little one plot so that I could show you. But we haven't really, analyzed the whole thing and reach some conclusions yet. But we'll see how far we'll get. Of course, I don't think for this audience I need to motivate the need for solving collective action problems, but it's kind of nice to have some examples in our mind of what actions could be, not just how the opinions are distributed, but how they result in actions. And I think we could think of, for instance, climate change and mitigation as a coordination problem. So if a single individual takes some action, that doesn't prevent, any tipping points. So it's kind of you need a bunch of people to actually, or countries, to actually act so that you can reap the benefits of that action, or at least the avoided costs. Or for instance, COVID, which I guess we always have to refer to in these times, where if a single country decides to close borders or close traveling from a particular country, that doesn't give you any benefits because people just go around. So you need some coordinated efforts to get some benefits from your decisions. So again, we devise the most stylized collective action problem that you can get to kind of get a real sense of what's going on. And here we have, again, two choices. Either you can decide to go for a safe choice that presents no risk, which can constitute just business as usual, and that will give you a baseline reward, one. And then you have a risky choice that really takes this coordination. And in this risky choice, if none of the others decides to take this risky choice also, then you don't get any benefits, so you kind of lose this baseline reward. But if enough people go for this risky choice, actually everyone is better off, and they all get a reward O that is bigger than the baseline reward. So it's in everyone's interest to actually coordinate into this desired state. That's how much they lose. You could think, that's why you could think of this risky action as a cooperative action, right? Because you are enabling others to also reach their highest rewards. And then again, as I said, this is a nice case where everyone is, it's actually in everyone's interest to coordinate into the other state. It's just that it might be hard.
Can I ask a quick question?
Yep.
Just to make sure I've understood. So there is no penalty, it's always the reward in your model, right?
Yes and no. Of course, there is the chance that you lose the base reward, so you could see that as a penalty. I guess I could frame it as a cost, but like if I shift everything down. But here, let's say if you go for the risky option and others don't, then you don't get the baseline benefit. So you basically lose 1 unit, right?
Yeah, no, I got it now. I was, I guess, more confused about the term risky because you're expecting the blue line also maybe go
a negative. Yeah. It's just shifted up. Yeah, but you're right. But no, of course, we want to relate this to this distribution of opinions, and the simplest way we thought about doing this was to just say, okay, your opinion will actually lead to some different valuation of this outcome of coordinating. So now you can think that your population has some bimodal distribution. You can control this bimodal distribution of opinions, and that bimodal distribution of opinions just influences how much each individual perceives that they will get out of this interaction. And then, of course, because you need to know what others are doing to kind of decide, right? You need to estimate what others will be doing, and you do that by looking around your neighborhood. So, of course, if you see that a lot of people, or if you think a lot of people will not contribute, then you should probably not contribute. If you think, or if they choose the baseline option, and if you think a lot of people will choose the risky option, then you will want to contribute. So this, you just follow the baseline process. So you look around, you compute your expected payoff based on your what you see around you, and then you compare the payoff of choosing one strategy versus another. If the payoff of a strategy is higher, then you have a high probability of adopting that one. If it's lower than you already have, you just stay with the same strategy. And then, of course, to relate this with effective polarization and to what we saw before, you could think of the belief being formed based on the information that you get. And if you have a well-mixed population, so that there are no real groups, then you get information about what everyone else is doing. But if you have a more modular structure, then you can have kind of two groups, group A, group B, and you'll get information that is based on your neighborhood. And of course, there's an interaction between effective polarization and issue-based polarization, which corresponds to what we saw before, right? Because we could have a distribution of opinions that is spread throughout the network, where blues and red could be anywhere, or we could have a kind of sorted distribution of opinions where blue are in one side and red are in the other side, on the other side. So like this, we can control the distribution of opinions, we can control how segregated they are, and we can control how sorted the distribution of opinions. And if of course, the result, because this is a coordination game, the results will depend on the initial fraction of people signaling, for instance, R. But we expect to see some differences for the different scenarios. So we'll have these 5 scenarios where you have, well-connected population and everyone has the same valuation. So there's no distribution of opinions. And then we'll see how polarization just in opinions affects the ability to coordinate. Then we'll segregate them and then we'll sort them. And what you see, you can compute, for instance, the total welfare. So if you think that everyone is just going for the safe bet, they will get a payoff of 1, right? And then if there's miscoordination, then some will lose and then they won't be able to coordinate. So you'll get a lower than 1 payoff. And then if they actually succeed, they'll get a payoff that's higher than 1. So what we see is a perfect rank, or pretty much perfect ranking of these options. So the well-mixed homogeneous valuation is ideal, and then heterogeneous valuations of the outcome kind of give you less chances to coordinate. But then when you start segregating that you get the real problem. So the effects associated to the network are the most important ones. And if you combine these two, segregation and sorting, which is what is characteristic of affective polarization, then this is when you start really getting a collapse in the ability for the society to coordinate into an option that they all desire. So this is kind of an extreme case, right? And we can actually prove some interesting facts about the distribution of valuation. So actually, it's not necessarily bad that you have a non-homogeneous distribution of preferences. It's actually you can actually prove the existence of a non-homogeneous distribution of valuations, which relates to a lot of the research that's been done, showing that having diversity of opinions, diversity of people leads to an easier time in achieving collective goals. And then we can start doing interesting things like segregating and having a dynamic process that co-evolves the behaviors and opinions with the network structure. And then what we see is that, well, that optimal region here I didn't go in detail, but here we're basically manipulating the distribution, if it's more bimodal or less bimodal, and the blue regions are showing you this existence of a sweet spot for ability to coordinate. But then if you add segregation, then you see that sweet spot gets narrower and narrower. And it actually becomes closer and closer to a homogeneous distribution. All right. So before I show you, I thought I had some experimental results. Yeah, so we actually did experiments with people where we gave them this game to play and gave them full information about others' opinions, so how much they value the payoff, because we can control that, and then gave them partial information and partial biased information, and we see kind of these are preliminary results, but it seems that the high value players, so those that really that have a high benefit for going for the nice option, they respond really well to this. Well, really well. They respond according to the model. The low value players, their response, well, there is some decrease, but it's not so obvious. So there seems to be some optimism bias, right? They think that others will, even though they don't have information about what the high value players, they seem to think that others will cooperate, which leads us to the final part, and I'll just glance through it, which is the effect of exactly having these biases in the information that you get. And these biases are not just a product of the network, but you could imagine that they exist just naturally because humans are, biased. And a lot of, well, I'm going to skip through all of this. And there's, evidence from 1976 saying that, yeah, it's expectation and biases in expectation that almost determine your action. And there is an interesting feedback. It's part of the stylized facts about cooperation that said that people who think others will cooperate are more likely to cooperate, even when you're not playing a coordination game. So even if it's in your selfish interest to defect, if you think others will cooperate, you are more likely to cooperate. So there's this very nice examples about how people have strong biases into what they believe others will do. And that might be through the local information that they get, as we saw in the previous part, but it could be more generally just a part of human nature. Here, I think this is a really interesting example where you, at some point, when was it? In '99, there was some hurricane in Princeton that flooded a water treatment facility, and the university advised the students not to shower so they could save some water. And then it's quite interesting. A couple of students from psychology, they started asking in the cafeteria other students, well, if they showered or not, and how many students they thought were showering. And here, showering is kind of the defection action, right? Because you're using the water that they don't have. And it's quite interesting. You see that those that, the actual fraction of people that reported having showers was 33%. And then those that did not shower thought that 39% of the people showered, so a little bit more. And those that did thought that 63% showered. So it's quite interesting. They are both biased in the same direction, but the bias effects is quite different from the different actions. And again, in climate change, this is also very, very clear that we have a lot of biases. If you ask people, is global warming caused by human action? This is the real fraction of people that actually do believe that it is caused by human action. And if you ask them what they think others think, then they completely underestimate both those that disagree and those that agree. And here, for instance, it's in China, if you ask people if they should sign a treaty to cut down by 90% their emissions, you get an actual value of, well, pretty much consensus, 90% of the people think they should. But if you ask them about what others think or what they think others think, you get a very strong negative bias. So in general, what we did was that we designed this range of possibilities for the different biases, and we found in the literature evidence for the different kinds of biases. So you could think of the simplest case where both those that cooperate and those that defect, they kind of think that there are more cooperators than there actually are. So if X is the reality, the orange line is what defectors think there is. The blue line it's what cooperators think there is. You can design this for scenarios. So over trust, everyone thinks there are more cooperators than there actually are. Under trust, there are less cooperators than there actually are. And then the literature also has some evidence for these other two scenarios where you have pluralistic ignorance, where you think that you're the only one that is doing what you are doing. And then there's also the false consensus where you think that everyone is doing the same thing as you. And then I'm just gonna show you, I guess, this one here, where you see that we have basically different regions. So here they face again a coordination game, and what you find is the existence of these interesting equilibria where the population is kind of stuck in the suboptimal behavior. So they neither coordinate in the safe option or in the good option. They're stuck doing the wrong thing and having suboptimal outcomes. And so this is really important, because if we think of, for instance, policies to change behavior, we can test, for instance, the role of fines, and we see that here, for instance, this is the group success and some fine on defectors. And you see that if there is some undertrust, so if both of them think there are less cooperators, then you basically need a fine that is the same scale as the cost of your cooperation action to get some outcome. Whereas if you provide some information, then you can really, by changing this bias, so this is the outcome without any bias, then you get cooperation even without any punishment. So providing information is kind of a nice mechanism here to prevent the bad things that biases cause. All right, so I guess I'm just gonna conclude and kind of recap on the things that I said. So we found these really nice properties of propagation of opinions, and we showed that depending on how these processes of contagion of opinions occur at the level of individual, we can have different types of polarization or no polarization at all. And then depending on how these opinions are distributed, and so on the types of polarization that we have, that can be good for coordination or it can be very detrimental, especially when you have the kind of affective polarization that segregates individuals into groups, but also generates these bubbles of opinions. That is particularly true because it creates these biases, and in turn, these biases, whether they're from the network or they are human, intrinsically human, they can lead to very suboptimal points for coordination. So providing information and manipulating or trying to manipulate how these networks are connected is crucial, many times even more efficient than actually trying to find, to punish individuals in these networks. All right, thank you for listening. I'll take some questions in the last 2 minutes.
Thank you very much. Yeah. Does anyone have any questions? I can see that there is one here. Yeah, please go ahead, Han.
Yes. So just from in the beginning, you showed this figure on polarization in the US, where the conservative and the Democrats separated more and more. And important here is that this is also a within person phenomena. So people can move over a dimension. They can be, so polarization is also a individual characteristics. People can be more extreme. But in all your models, your opinion is a discrete variable. So you have either opinion A or B. And there's a whole tradition in this opinion dynamics models where there are continuous opinion variables. Yeah. And yeah, don't you think that that's necessary to get the dynamics that you need?
So in fact, well, yeah, for sure there are interesting questions that come from considering a continuous. We do have some work on continuous strategies. I think we were trying to go for the most stylized thing we could do. Actually, when we started this work, we were interested in technology adoption more than opinions. So you can see that the first kind of work is more related to technology, and the data that we found was focused on technology, but it really elucidates a lot of properties of these systems. One thing that we did to create a more continuous system that is very important is to have kind of an intermediate state. So the nice thing about the continuous process, or the structural thing about having a continuous process, is that you cannot jump from one side to another immediately. You kind of have to diffuse, or you have to pass through intermediate states before you can reach the other side. And this really has to do with this intrinsic process that you were describing at the individual level. So if we do include this intermediate state, then we're able to recover most of the results that come from having a continuous description. So instead of looking just at the A and B, we have A on one side, then we have kind of a 0 in the middle, and then C. If you get that, that's the minimum ingredients that you have. But the conclusions that regard, the effect of networks are kind of the same. But to say that in this case for the action, the coordinated action model, we did use a continuous distribution. So we actually used, basically we have two Gaussian distributions that we can manipulate. And we individuals have an opinion that is something in between. Could be anything in between 0, or in this case, 1 and infinity.
Okay, thank you. Maybe I have to go, but
okay. Oh yeah, it's time.
Janus, you have a question?
Yes, thank you. Actually, I have 2 questions, but we'll see if we get there. Thank you very much. That was a very interesting talk. The one thing I was thinking about the whole time is that you treat sort of the network structure as given. So it remains fixed throughout the process. But I think if you look at experiments, there is some sortativity that's happening between nodes. So edges are being removed and added depending also on opinion. And of course, with a discrete opinion model, that's maybe difficult. But if you include a continuous model, then you could say as soon as opinions diverge to a certain extent, you start to consider to sever edges. And so you can actually start with maybe a complete model and continuously, or this becomes slowly deformed into a sort of 2 community network. I was wondering if you thought about that interplay at all.
Yes, we did look into that. In particular, we were able to get some analytical leverage where you consider 2 modules that have a connection between them, and you can track the evolution of this connection between the 2 modules. And actually, I think I did have some. Well, I think it's here. So here we actually have a network we tried 2 configurations. One in which you break links or you rewire based on the distance of your opinion to the opinion of the other nodes. And the other that was based on the distance of your action. Well, in this case, if your action was different than the action of others. And the results are kind of intermediate, are the combination, are the superposition of the results that we found when we considered the 2 independently. So as your network develops, if your update rule for the network develops these clustering, then you start getting the results from the clustered network. If it doesn't develop and it remains well mixed, then you get the results for the well mixed. which I think it's a really, and I agree with you, it's a really important question, because now it's really about, it's not just about whether polarization is good or bad, but it's also about how it influences the network structure, which in turn is what determines if it's good or bad. And so there are some really interesting questions in that at that level.
Yeah, thanks. Maybe a short second question. If I'm interpreting this public goods game correctly, where you have the baseline action and then either a reward or a sort of effective loss, then is it correct to sort of, I'm trying to frame this in the idea of a prisoner's dilemma game. I don't know if that's a correct interpretation, but I'm wondering, in that literature, there was some people talking about the snowdrift game. I don't know if you've heard of that.
The what? Snowdrift?
Snowdrift game. Yeah. So where even if you sort of collaborate and your opponent doesn't, there is a, for example, climate change. If I change my habits, it's a minuscule effect, but whatever fraction of the population does do something, there is some effect that is positive for everybody.
Yeah.
And the incentive for not collaborating is to free ride in a way. I was wondering if that changes anything, if you have that sort of ordering of payoffs instead of the definite loss or effective loss in this case.
I'm not sure I really followed your question, but here what we have is a stag hunt game. So, which is really, it's this idea that you, well, if you both go for the, you can either go for the rabbit or you go for the stag.
Yeah.
If you both go for the rabbit, then you get some small reward. But which is better than you trying to go for the stag, but then someone else goes for the rabbit, and so you lose the stag and the rabbit and everything. So I think we believe, I guess, that the stylized model for climate change is a coordination game. It's a stag hunt more than it is a prisoner's dilemma. I'm not sure. The snowdrift, in the snowdrift, you basically want to do the opposite of what the other does, and I think that's fair above the threshold. So if you've already kind of committed enough to reach, to avoid the tipping point, then you really want to do the opposite of what the other is doing, because you don't want to, keep contributing to be above the threshold. So yeah, there's some interesting interplay there, where after the threshold, the game kind of changes, and that's really interesting. But I think for now we're still in this phase.
Clelia, do you have a question?
Yes, so it's probably a very, sorry, not so scientific question, but I don't know if you know about this social dilemma documentary on Netflix.
Yeah.
So I think, in the documentary, they were denouncing the use of machine learning in social network for, in the social network, they make money if people keeps on going to that social network. So if they want to keep the attention of the people, they are trying to feeding them messages that they like, so that they can, come back and look what's going on. And so in various social media, they are using machine learning in order to learn what people like, and then feeding them even more likable things. And so they're creating, in this documentary, they were denouncing the polarization that this was creating in the society. And so I was wondering if, if there is a way of quantifying the level of polarization of different types of social media, and if there were also a way of quantifying if this polarization was actually coming from this learning algorithm that would feeding you things that you like, or if it was coming from the modular structure of the network underlying the social media. For example, maybe Facebook is more modular than Twitter, or if it was coming from the type of messages that was there and that was destroying the trust of a certain side in the other side. So there are different factors in your in your models? And I was wondering if there is a way of quantifying all these different factors here.
Yeah, I think that's a great question. I know there are some people studying these, basically content filtering, which has to do with what I show you in these social networks, which I think is one of the things that you were saying. But there's also another kind of algorithmic intervention that these platforms do that has to do with how you recommend your friends. And so you can imagine that these two things have a very interesting interplay for creating these modular networks, and then for within these modular networks, the positions becoming more and more extreme. Yeah, but that's and the time scales at which these two things happen, I think that will be crucial for determining what happens to the population overall. But I don't know much about.
So there are definitively different ingredients that could be suggested to social network in order to prevent this polarization.
But they don't. Well, but the thing is, from a profit-making perspective, there are not a lot of incentives to wanting to prevent this.
I think they're discussing this a lot in the US right now, because there are some big. What's the name of this? I think they're. From what I remember, right now there are some how to say des procès. I don't remember the English going for that. There are some
procedures.
Yeah, no procedure. There are some big lawyer things and judges, and they are discussing what is the role of social network in the polarization of the American society, and they're discussing laws to somehow prevent social network to do this machine learning thing. But maybe there are other ideas that could be given to them, such as changing the modularity of the network, or
Yeah, I agree. And answering, I guess that also relates to Janu's question about the dynamics of the network. So it's kind of ambiguous, right? Because if we think of a social network as Clelia was saying, we can see the dynamic. The dynamics is so fast. We can see it in our real. We can see it. But the real social networks, let's put it that way, they evolve much slower, and so it's hard to say right now if the polarization comes from the social media network, or just from the whole combination of contexts that you have. And that's partly why we were also trying to go for just looking at different structures and not assuming necessarily a co-evolution of these two processes, because we don't know if polarization is just in social media or if it's in the real world. I mean, the survey seemed to indicate that it's in the real world, but the cause is still ambiguous.
Are there any other questions? Well, if not, then let's thank Vítor again for the really nice talk.
Thank you. Thank you for the invitation.
Yeah. And I guess we'll see you around whenever we can see you around.
Bye, everyone.